We already see the brief concept of energy in part 1. So we continue our lesson with part 2, which is potential. When we talk about potential, it always measured from one point to another point. It always called as a potential difference, which is the potential between 2 points. Let's say we have point A and B. So we rename the potential difference as a VAB. Potential difference also known as voltage. That's why when you want to measure a voltage, you have to connect your probe from one point to another point. So you can see or read the potential difference from the voltmeter. Next, we have absolute potential. By definition, the absolute potential is actually a potential with infinity as your reference. Or we can write as a VA infinity or only VA. And next we have a potential gradient. Potential gradient is a tangent or gradient of potential, which is delta V. From the potential gradient, we will later on see how can we relate the potential with the electric field intensity. Right, by definition, a potential difference, it is basically a total work done to move a unit charge Q from point B to point A in the field E. Let's say we have electric field E, and then we have point B and point A. We have a charge at point B, and we want to move the charge to point A. So potential is equal to energy divided by charge, or equal to negative QE dot dl divided by Q. So the equation can be simplified to VAB is equal to the minus integration from B to A E dot dl. Next, we see about the equipotential. What is the equipotential? Let E dot dl is equal to 0. This happens if your E field and your dl are mutually perpendicular, because the dot product should have a certain mutual directions. Okay, it should be parallel at best. Electric field is constant along surface perpendicular to E. Next, the line of constant electric potential are called equipotential. This can be explained by using this figure. Okay, you have three different figure. The first figure you have, the electric field, the constant electric field. Let's say you have here the negative Q, and here we have a positive Q. So we have the electric field, from positive to negative. So this is your direction of a field. Okay, let's say I draw some line here. Okay, you can see the first, second, third, fourth, and so on. Okay, this line is called as an equipotential. Okay, the electric field, okay, along the same line or the same equipotential will have the same magnitude and also the potential value. Okay, let's say we have a point charge at the middle and we have the field going out. If I draw few equipotential from a certain distance from the charge, we can see here. So the electric field as well as a potential along the equipotential will have the same magnitude. Please remember that. And last we have electric dipole. The electric dipole is not really popular, but you have to know what is electric dipole means. Electric dipole is basically we have the two charges which has a different sign. Let's say we have positive and negative. And this charge is located very near. And what is the characteristic of electric field? Okay, contribute by this dipole. So we will see later on. Next, let's see electric potential due to spherical charge. Let's say we have a sphere, okay, with hollow inside. The sphere have the radius of r and it has a surface charge on the surface of the sphere, and the total charge is equal to Q. By using Gauss' law, we can derive that the electric field on the surface of the sphere is equal to Q divided by 4 pi epsilon naught r squared. When moving away from the surface of the sphere, we can see that the magnitude of E is dropped by the factor of 1 over r squared. What happened inside the sphere? Hopefully you still remember when we draw a Gaussian surface inside the sphere. This Gaussian surface contains no charge. So the Q enclosed is equal to 0, resulting to the E equal to 0. But what happened to the potential? Right. At the surface of the sphere, the potential is equal to Q divided by 4 pi epsilon naught r. While moving away from the surface of the sphere, so we can see that the voltage drop, okay, by the factor of 1 over r. But what happened inside the hollow sphere? We can see from this graph, we have the value of potential inside the hollow sphere, which is equal to Q divided by 4 pi epsilon naught r, which is the same with the potential on the surface of the sphere. Why? This is the explanation. Basically, the relationship between the potential and electric field is equal to V equal to ED. Noted that when E field is equal to 0 inside spherical surface charge, V is constant anywhere inside the spherical surface charge. Okay, because delta V, so it's related to ED. So basically the V1 minus V2 will result to E equal to 0. So it means that V1 and V2 should be in the same value. Okay. Next, why determine electric potential? Energy is stored in E field. For example, during lightning strike, energy is transmitted through space by electromagnetic wave, and energy is stored in atomic or molecular binding. From electric potential, we can easily determine the electric field using gradient. We will see later on how can you use gradient to find the electric field if you are given electric potential, and vice versa. This is the relationship between electric potential and also electric field intensity. So E equal to negative gradient V. Let's see example 3. Find potential difference between A and B anywhere in a spherical coordinate caused by a point charge Q at the origin. That is the questions. Imagine you have a sphere and then you have a point charge at the origins, and I draw the dot line which have a different radius to pinpoint a location of point A and B anywhere within the spherical coordinates. Let's say I have the point A with a radius RA at that point, and then I have a point B, okay, with a radius RB at that locations. We can write the coordinate of A and B as RA, theta A, phi A, and then we have B, RB, theta B, and phi B. So the coordinate has the function of radius, theta, and phi. But you must remember that the potential on the equipotential surface is the same. That means we don't bother about the value of theta and phi. You only concern about the radius, where when our point of interest is further away from your charge Q, so the magnitude will decrease. The electric field due to the point charge is equal to kq divided by r square with a unit vector of r. This is what we discussed in chapter 2. Okay, and we can change k to 4 pi epsilon naught. So this is the general expression for E field due to point charge, as you know. And then to find what is the potential difference between point A and B, we use these expressions: negative integration from B to A E dot dl. And then you insert a E equal to Q divided by 4 pi epsilon naught r square, and our dl is spherical coordinate. We have the r in direction of r, this is the first element, and then we have r d theta in direction of theta, and we have r sin theta d phi in direction of phi. As we can see from our spherical coordinate, our E field only have r components, so therefore we won't bother about the theta component as well as phi components. And then when you solve the integrations, okay, we have dot product here, so the r component will be cancelled out. So our solution become q divided by minus q divided by 4 pi epsilon naught in bracket 1 negative 1 over r from RB to RA. So our solution will be VAB equal to Q divided by 4 pi epsilon naught in bracket 1 over RA minus 1 over RB. The unit is volt. Next, we go to example 4. Prove that the potential difference inside an electrostatic field in a closed path is 0. So you have to prove. Let's say you have a closed path and we have 2 points, point A and point B. Okay, we have the electric field, okay, around the closed path. And we have a path 1 from A to B, and we have the path 2 from B to A. When we solve the problem related to this closed path, so the closed integration of E dot dl is equal to the integration from A to B E dot dl plus the integration from B to A E dot dl. Okay, when I change the limit to be opposite, so the sign become negative. So we can see that this is the same thing. So the total integration, no need to solve, you know, this is equal to 0.